黎曼罗赫定理的同时，致力于全球数学交流。1941年，海蒂拉玛和安泰尔发明的调频技术落地于无线通信系统。1965年，戈登摩尔总结实践经验，提出了一直被追赶的摩尔定律。2000年，高空推动建成世界上第一条1公里长的光纤网络。1986年，杰弗里·辛顿将反向传播技术应用于深度学习。科学研究和技术发展就是这样一步步向前迈进。链接实践和整合资源，积极探索和开拓创新，讨论碰撞和相互激发，人才发展和融合生态。查斯乌科技网站汇聚全球高价值科技和学术信息，提供多种模式智能高效服务，链接全球学术、技术和人才资源，链接、创新、激发、融合。查斯乌科技网站与你携手并肩，共同促进全球科学和技术的进步。科学和技术的进步源自于什么？是在实践中的启示，是在探索中的火花，是在碰撞中的激发，是在融合中的升华。1654年，帕斯卡和费马在分补助问题的讨论中，开启概率论的大门。1687年，牛顿在哈雷的鼓励下，积极研究并最终出版《自然哲学》的数学原理。1736年，欧拉走过哥尼斯堡七桥，并开创图论这门新的学科。20世纪初期，爱因斯坦和波尔在相爱相杀中，分别开拓广义相对论和量子力学。1936年，图灵在研究可计算数的过程中，开始图灵通用机的探索。1945年，参与了曼哈顿计划的冯诺依曼带来计算机领域的3定律。1948年，香农在和冯诺依曼的讨论后提出信息熵和香农定理。20世纪初期，菲尔兹在证明黎曼罗赫定理的同时，致力于全球数学交流。1941年，海蒂拉玛和安泰尔发明的调频技术落地于无线通信系统。1965年，戈登摩尔总结实践经验，提出了一直被追赶的摩尔定律。2000年，高空推动建成世界上第一条1公里长的光纤网络。1986年，杰弗里·辛顿将反向传播技术应用于深度学习。科学研究和技术发展就是这样一步步向前迈进。
Hello, everyone. Welcome again to our Charles Park OTF-SIG online seminar series. And today, we are very honored to have Professor Hossein Arslan from Istanbul to give us a talk on the back to basics, forward to 6G, reinventing OFDM for unified air interface. I'm going to give a quick introduction to Professor Arslan. Dr. Arslan is an IEEE Fellow, NAI Fellow, and a member of Turkish Academy of Science. He received his bachelor degree from Middle East Technical University, Ankara, Turkey in 1992, and his master and PhD degrees from Southern Methodist University, Dallas, Texas, in 1994 and 1998, respectively. From 1998 to 2002, he worked with Ericsson on projects related to 2G and 3G wireless communication systems. He then joined the University of South Florida, where he served as a professor in the Department of Electronic Engineering from 2002 to 2022. In 2013, he joined the Istanbul Medical University to found an engineering college, where he currently serves as the Dean of the School of Engineering and Natural Sciences. Dr. Arslan has also held several industrial and national advisory roles. He has served as the consultant for organizations including Artis, Salvernik, and Tobitech, and was the founding chairman of the board of directors of ULAK Communication, Turkish telecom equipment provider. He also served as a member of the Tobitech scientific board, and from 2021 to 2024 as a member of the board of director of Turkcell. His research focuses on various communication systems, particularly physical and modem access layer technologies. His current interests include 6G and beyond radio access technologies, physical layer security, interference management, cognitive radio, beyond OFDM multi-carrier systems, dynamic spectrum access, non-terahertz communications, and joint sensing and communication. He has collaborated extensively with leading industrial partners, including Interdigital, Aritsu, NTT Docomo, Nathan, Honeywell, Aslan, Vatzel, Turkcell, and K-Side Technologies. There's many collaborations, which is very impressive. In addition to his research, Dr. Arslan has made significant contributions to various communication education. He has developed several courses at the University of South Florida and Istanbul Medical University, including various systems laboratory course and supported by the National Science Foundation and Keysight Technologies. He has also served in various leadership roles in IEEE conferences and on the editorial boards for several major journals, including IEEE Communication Surveillance Tutorials, IEEE Sensor Journals, IEEE Transactions on Communications, and IEEE Transactions on Cognitive Radio. Okay, without further ado, please join me to welcome Professor Arslan for today's talk.
Okay. All right. Thank you, Shangyang. I'll share my screen.
Sure.
I hope you can see my screen, everybody,
Yes.
and then you can hear me well.
Yes.
So again, this is Hüseyin Arslan. First of all, I'd like to thank Shangyang and all the organization committees for the invitation and for giving me the opportunity to present today. So my talk is, I don't know whether it's interesting to many of you, but it's very dear and near to my heart. It's going to be back to basics because it's a topic that's not new, something that I myself have been working over the last 30 years. But it is so critical, which will shape 6G and beyond. So we are going to be revisiting and reinventing OFDM as a unified air interface for 6G and beyond communication standards, not only from a 3GPP perspectives, but also for other wireless standards like Wi-Fi and other, low power wide area networks as well. So this is my email address in case you need to get in touch with me with some questions. This is my WeChat number, and this is the website of my group. So as Shangyang mentioned, this is just one slide snapshot of my CV. As you can see, half of my life is in industry, the other half is in academia. So from that perspective, my talk is going to be more applied research, and things are actually from the perspective of the standards and also from the company views of waveform rather than academic view for today. because I'm sure you have had presentations from other colleagues focusing on all these academic aspects of waveforms. But today I will focus more on practical aspects and from a company perspectives. So this is the outline of my talk. I'll briefly talk about the expectations from 6G, use cases and applications, and the requirements on waveform design because of these new applications and use cases. But the question that we need to ask ourselves, it is a question actually everybody's asking, a very important question: do we need a new waveform for 6G? So I will try to answer that question because I think many of you are going to be interested in this, my answer, my perspective. And I will also mention a few things about waveform standardization, 6G, 3GPP aspects, where we are, and what are the critical things that's being discussed lately, because the standards have already started. And the number one thing that we need to decide is the waveform and frame structure. So what are we discussing? What are the company views, different companies? I'll talk about that. And this is actually the main part of my talk, OFDM and DFT-spread OFDM. It is not a new thing. So why are we still talking about this? The reason that we are still talking about this is because companies are pushing this for the 6G standard. And it's not something that I'm proud of. It's not something that I really like, but that's the way it is. That's why it's an old problem, but there are new perspectives because 6G is a new standard. 6G comes with new requirements. So how do we solve 6G problems, 6G requirements with old technologies? And what are the challenges and what are the opportunities? That's what I'm going to talk about. And of course, there are some things that if time permits, I can touch upon. I have more than 200 slides. It can take the whole day, but I don't want to take your whole day today. But let's see how we can move forward. I'll try to cover as much as I can. One of the things that I like to talk is, what are the lessons that we have learned from 5G waveform? Whether 5G waveform was successful, did we achieve our goal with 5G waveform or not? I will try to give my perspectives as well. And when we are talking about 6G, as always, backward compatibility is important. So that means that 6G should be compatible with 5G, and that ties our hands. So what are the strategies that we need to do in that aspect? And also forward compatibility is very important because 6G standards, the base standards, are things that we are focusing now, but there will be new releases, and of course at some point there will be 7G and maybe more. And whatever we decide for 6G, is it going to be suitable for the further growth in terms of forward compatibility? That's what I'm going to talk about as well. And flexibility, Isaac, as you all know, is a very hot topic. Everybody's talking about sensing integrated with communication. And so far, our waveform design was basically on communication perspective, from that perspective. And sensing and radar has their own waveforms, especially impulse radios and also FMCW signals. So when we design actually to integrate this communication and radar and sensing, what should be the waveform and what are the new requirements? This is something that I will try to talk about. And also hybrid waveforms and waveform domain nomad. So where do we go from here? That's the question actually that we all ask. I mean, where are we and where do we go from where we are? So before I get started, let me just describe what the waveform is, because everybody has a different understanding of waveform, what the waveform is. Many people think that waveform is a shape, it's a pulse, physical pulse. But actually, waveform is more than that. So waveform is pretty much the signal, the physical signal that we transmit. So it includes, the lattice structure, the grids where we, put our datas, the symbols that we want to transmit. Where do we put them? Where do we deploy them to generate that physical signal? So at the end of the day, there is a resulting signal, time signal that we transmit. But how do we generate that signal from the data? And what is the process that we do? And not only a signal for a single user, if there are multiple users that we need to really place them into this grid, into this physical signal, how do we map all these different users into this structure? And not only in a single link, but if we have uplink and downlink, so how do we manage this physical signal, physical structure to allow signal transmitting from downlink and uplink with minimum interference? And also, how do we pack data together with the pilot? Especially sensing is very critical now, and we need special pilots for that. We already have pilots in our communication system, but how do we design all these things, and how do we generate that physical signal to enable all these functions is part of the waveform. So waveform is very generic. Waveform is basically defining how to transmit the signal, the data, the pilots, the user's information, where to transmit them, and all the process that's related to create that physical signal in downlink and uplink is the waveform. So it's a very generic. If we do it properly, everything is going to be easy. Everything is going to be smooth. So that's how we should look at the waveform, not just a shape, physical pulse shape. So from that perspective, waveform has a very rich and long history. So I didn't look at the deep history, but if you look at the historical evolution of waveform from the standards perspective, from the first generation until the fifth generation, we have used different waveforms depending on our requirements, depending on our rates, data rate, the bandwidth, and channel conditions, the range of the communication. We end up finding the best waveform, the most optimum, the most proper waveform for enabling those requirements. So, of course, the requirements has changed in time. So, in the earlier generations, voice was the main application, and the bandwidth was very narrow. Frequencies are low. So, we developed proper waveforms, mostly single carrier. If you look at the early generations in American digital system, Pacific digital system in Japan and America, we use Nyquist and orthogonal pulses, race cosine pulses. They were overlapping in time. The channel, because the bandwidth was narrow, less than the coherence bandwidth of the channel, so we use flat fading channel. We had no dispersion, so sync pulses in time domain were appropriate, and they are overlapping as well to maximize the spectral efficiency. And we added guards to protect against adjacent channels. So no equalizer is needed. But later, when we increased the bandwidth in GSM, 200 kilohertz compared to 30 kilohertz in American digital and Pacific digital. 200 kilohertz was more than the coherence bandwidth of the channel for the range of communication. Then we couldn't maintain the orthogonality of the sync pulses. Therefore, we end up using overlap in time domain overlapped shapes, okay, Gaussian shapes rather than raised cosine shapes. So we allowed overlapping. So from that perspective, GSM signal is considered as non-orthogonal single carrier waveform. So we basically allowed some non-orthogonality, which is managed by equalizers at the receiver. So we used a little bit more complex receivers at the receiver, but manageable with the processing that's needed. So that was the strategy. And then, of course, later in 3G, 2.5G, we used spread spectrum systems, direct sequence spread spectrum CDMA, and the strategy was different there. So in 4G, started with Wi-Fi, later with WiMAX, fixed WiMAX, and also nomadic WiMAX. We end up using OFDM waveform. OFDM was very powerful from spectral efficiency perspective, and also was very suitable for static channels, where it allows us to control the carriers. If they are narrow, we can really control them and then populate them with the proper modulations. So it was very intriguing. And again, it was started with DSL, ADSL, where the channel is fixed. And then later with Wi-Fi, again, the channel is more or less fixed or slowly varying. And then fixed WiMAX, the channel is again fixed. And then nomadic WiMAX and mobile WiMAX, but the channel is slowly varying. So there we applied OFDM successfully, and then later we developed this LTE standard 4G, and then we basically steal the idea from there, from Wi-Fi and WiMAX, and then deployed OFDM in 4G. Of course, cellular standards are mobile, and the mobility can change. And we used OFDM in mobile environments. We end up having interference because it's not really suitable for mobile. And then we end up solving that problem. We didn't fix the problem, but we kind of find a solution using link adaptation. When there are high mobilities, we reduce the data rate. We use low order modulation. They are robust against noise and interference. So that's how we handled. In 5G, we developed a new mechanism, which we call it flexible OFDM, multi-numerology OFDM, where we change the OFDM structure a little bit, depending on mobility, depending on the latency requirements, because 5G came with different requirements. High speed, low speed, high data rate, low data rate, low latency, medium latency. So we had various requirements. Therefore, we end up using a flexible waveform. We needed a flexible waveform, so we generated that flexible waveform from the mother waveform, which is OFDM, by changing the carrier spacing. And if you ask me from the 5G perspective, from that waveform perspective, from flexibility perspective, we generated a strategy, but that strategy didn't work, so we failed. So I think maybe I should just say the last thing that I want to say first upfront. 5G OFDM, multi-numerology OFDM, is a failure from my perspective. I'll talk about that in a minute. So if you compare the waveforms also from different links, uplink and downlink, up until 3G, we used the same waveform in the uplink and downlink. We didn't change the waveform. In 4G, we used single carrier in the uplink and the OFDM in the downlink, because OFDM is not power efficient. It is spectral efficient, but single carrier is power efficient. So in the uplink, power efficiency was critical. In the downlink, spectral efficiency was critical, because the data was, the demand for the data was asymmetric, the rate. So we needed more downlink high rates compared to uplink. But in the uplink, we needed more energy efficiency, because the mobile devices are battery operated, and they couldn't afford, OFDM type of waveforms because they consume more energy. So that's our strategy. We have different waveforms in different links. In terms of lattice, 1G, 2G, 3G, and 4G, all these generations, we use fixed lattice. The lattice structure was fixed. In 4G, actually, we can call it a little bit hybrid waveform because ranging channels used CDMA, other channels used OFDMA and single carrier FDMA. And since it is a hybrid waveform, we had to use some guards between the different resources. If the resources are using CDMA, they can create interference with the other resources that are using OFDMA. So we minimize that leakage by adding some guards in frequency. Also, lately we also had cell site adaptation. Different sites use different parameters like CP length, because CP is used to provide robustness against the delay spread of the channel, and the delay spread is related to the cell size. Longer distances create more delay spread compared to small cells. So we end up using different CPs with different cell sites. So it is like adaptive OFDM. So one of the also unique features of 5G is, like I said, is in addition to flexible CP, we also use the flexible numerology. The carrier spacing and OFDM symbol duration was flexible. So these are some of the things that's very fundamental. So I'm going to skip this. But now in 6G, things has changed. Those of you who are attending conferences and also standard meetings, 6G is bringing new concepts and trying to solve problems that accumulated in 5G. One of the problems that has accumulated in 5G, which we couldn't solve, is the IoT. We could never make IoT a success with 5G. And this is one of the things that we want to fix in 6G, better IoT, unified IoT. Also, in the late releases, release 19, we integrated sensing into the communication, but in 6G, we want to unify. So there is going to be one structure, waveform structure, frame structure, that can do sensing and communication optimally, so unified sensing. So when we design 6G, we want to make sure that that serves both sensing and communication, not communication-centric, not sensing-centric. So that design should be a unified design. So this is very important. So when we are talking about 6G waveform, we have to make sure that that waveform is suitable for both. Also, in 6G, we are talking about AI in day one, so native AI. So when we are designing a waveform, we have to make sure that it is AI compatible and that waveform will enable some of the AI features in different layers, physical layer, MAC layer. And the waveform should be flexible, cognitive, and it has to be because the RAN requirement and many slicing that we will generate from radio access networks will depend on the flexibility of the waveform. If the waveform is not flexible, we cannot generate proper slices. And slices are very important, RAN slicing, because we have wide variety of applications and wide variety of channel conditions. So it's very important that our waveform supports that flexibility and supports various slices. Similarly, the energy is very important topic in 6G, maybe the most important topic. Anything that we design from modulation, from waveform, from frame structure, from pilot structure, training sequences, everything should be energy efficient. So our current networks are consuming almost 3% of the global energy. 3% sounds like a small number, but if we increase the data rate by order magnitude, like 10 times more compared to 5G, and also the number of devices, if it increases by a factor of 10 times 10, 100. So that 3 becomes 300. So we don't have that level of energy. So we have to make sure that we develop our waveforms and the networks to consume less energy. So we'll talk about that if time permits. Coverage has always been an issue in our terrestrial networks. So we need to make sure that we have better coverage, better capacity, better spectral efficiency in 6G, and they are all related to the waveform design. Similarly, coexistence and dynamic spectrum access. There are new spectrum allocated for 6G, but there are incumbents there. So we need to make sure that we can coexist with them. And also coexistence with the previous generations. So 6G should coexist with 5G, but 6G should also coexist with other networks, with other technologies peacefully without creating interference. And things that we ignored in the past, the networks are not resilient, especially when there are disasters. So we need to make sure that 6G is more resilient. Another very interesting thing that comes with 6G, I'm sure everybody knows this, heard about this. In 6G, we are trying to unify terrestrial and non-terrestrial networks. Not only unifying, possibly we are going to be served, mobiles will be served simultaneously by both networks. So multi-connectivity. So a device will connect a TN base station simultaneously with an NTN base station. How do we do that multi-connectivity with such a large differences in channel conditions, in power conditions? That's a very difficult problem. And one of the main show blocker there is the waveform design. So we need to make sure that our waveform can support a unified TN and NTN structure. And of course, MIMO is important. So any waveform that we design should support MIMO in practical conditions and physical layer security. So since we are going to discuss OFDM in detail, I think it's very important that we all agree on OFDM. What are the capabilities of OFDM? Why OFDM is being used for 4G and 5G? Why we didn't give up on it? So this slides basically summarize OFDM in one slide. OFDM is an orthogonal waveform, as the name implies, orthogonal, and we have multiple carriers. So the total band, transmission band, is divided into several sub-carriers, which is good actually because the bands are increasing much bigger than, larger than the coherence band of the channel. We are talking about 20 megahertz and 400 megahertz, eventually 1 gigahertz, several gigahertz of bands that we are going to be using for transmitting signals for multiplexing users. So with such a large and wide band, transmitting a single carrier signal is not easy because, like I said, it's much bigger than the coherence bandwidth of the channel. Therefore, OFDM is very suitable in broadband communications, where we can divide the channel into smaller subbands and control all these subbands any way that we like. So that's one of the beauty of OFDM. It's a multi-carrier, but all these spectrum can be controlled easily in terms of power, in terms of modulation, in terms of scheduling. So we can manipulate actually any way that we like all this spectrum, because it allows you a large degree of freedom So that's the beauty of OFDM. I mean, of course, there are other things like, equalization, one-tap equalization, and, robustness against delay spread, and things like that. But from my perspective, I think the most critical thing in OFDM is the granularity in the spectrum and the ability of controlling the spectrum in terms of, again, link adaptation, modulation, power adaptation, and also scheduling. And there are some other advantages as well, which are listed here. But there are some disadvantages, as I will talk about in a moment. Now, let me start with some claims. Okay, these are very bold, aggressive. Some may not like it. Some may agree with me. We can discuss about this during the question and answer. But here is my claim. The first claim is 4G OFDM, which is LTE, and 5G multi-numerology OFDM, which is flexible OFDM that we use currently in 5G. They are not good. For 6G, they were good at the time. Like, LTE, I'm not saying that LTE is not successful. LTE is successful given the requirements of LTE, given the time that we have used it. We have, the applications that's required. OFDM was good, okay? There are some problems, again, with the mobility, and we solved those problems with, with some link adaptation techniques. So I'm not saying anything wrong or anything bad about, 4G OFDM. 5G OFDM, I can say the same thing, okay? Which is multi-numerology OFDM. I think this is not good. We failed, okay? So it's limiting. So it wasn't really a successful choice to use multi-numerology OFDM in 5G. We used it, but we failed, okay? So that's a bold statement. Now, in 6G, which is more aggressive than 5G in terms of the applications, in terms of the requirements, in terms of expectations, what we want from 6G, using the same waveform is not going to work, okay? So that's why I call it limiting, okay? OFDM, multi-numerology OFDM, is not the right waveform the way that we apply currently, okay? So it's not waveform. If we do that, 6G is going to be a failure, like 5G, okay? So it's not going to work. So another claim is 5G OFDM, multi-numerology OFDM, is not forward compatible beyond 5G applications, beyond 5G channel conditions and network deployments. Because in 6G, we are changing our networks, especially, we want to have multi-connectivity rather than a single base station talking to a mobile. We want multiple base stations simultaneously talk. FDM, the way that we are applying, is not suitable for this. And then we have new channel conditions like NTN, new mobility conditions, and OFDM is not going to be good for these conditions. So in summary, if you use the same waveform that we used for 5G, I don't think we are going to have a good 6G. So 6G is going to fail right away. We shouldn't even have a 6G. Again, if we think that OFDM is a waveform is the base of a standard, which I think it is, if you want to develop a standard, if the foundation is not good, which is the foundation is the waveform frame structure, if the foundation is not strong and good, that the rest of the structure is going to collapse, okay? So the foundation of any standard is the waveform, okay? If the waveform is not selected and is not designed properly, then the rest of the standard is not going to work. So let me support that. First, we talk about 6G being power efficient, energy efficient. OFDM is not power efficient. OFDM is not energy efficient. We talk about 6G being flexible in terms of duplexing, sub-band full duplex, in terms of multiplexing, in terms of other things. OFDM is not good because OFDM has a large power leakage. So you can't squeeze OFDM into, into a neighborhood in a spectrally efficient manner, unless neighborhood is orthogonal with whatever you are squeezing in. So if you can maintain the orthogonality of all the users, orthogonality of all the transmission, uplink, downlink, multiple users, multiple connections, then you can still use OFDM. But maintaining that orthogonality requires very strict synchronization, and it is almost impossible to do it with the complex structure that we have right now with the requirements of 6G. Therefore, out-of-band leakage of OFDM is not going to be good for these requirements. And it's related to the synchronization issues, NTN, multi-connectivity, and massive IoTs. Still, OFDM is going to be a problem. High-speed applications, so far, it was okay because, we used some techniques to avoid the interference. But, when the speed is increasing, like satellites, like high-speed trains, and the Doppler is creating a big issue, and the service becomes non-uniform. So, some users are going to be using very low order modulation, and some other users are going to be using, 64 QAM, 256 QAM, 1K QAM, 2K QAM, but some others are going to be using BPSK and QPSK. So you can't, provide the same level of service for all these users. So we need to make sure that all the users, whether mobile or non-mobile, they have uniform services. Like I said, INI interference is a big problem in multi-numerology OFDM. That problem is going to get bigger in 6G if you use the same multi-numerology. Multi-connectivity is required, maybe not, with TN and NTN together at this point, but eventually we want both NTN and TN base stations to serve a user, but it's going to be impossible today with OFDM. We will have new channel models and estimation. So massive MIMO and multi-connectivity, we don't have enough pilots now. We can't estimate the channel. If we use the same models, channel models that we have used today, if we use the same pilot methodology that we are using today, OFDM is not going to do it. Okay, so we need to develop new schemes. Again, security is also not, OFDM is the worst waveform in terms of providing physical layer security because, it's very easy to eavesdrop and it's very easy to also, jam OFDM signals. So from a low probability of intercept and low probability of detection perspective, OFDM is not the appropriate waveform. And also there are other issues like hardware and phase noise in high frequencies and multiple accessing and duplexing, especially in the uplink and near-far problem are some of the issues that we experience with OFDM. And there are some also other issues that we are going to face. For example, I'm not sure whether OFDM is the right waveform for integrated communication and sensing. You can do sensing together with communication, no problem, but I'm not sure whether that's the optimum solution. Also not sure whether OFDM is flexible enough, even though there are some things that we can do. We can adapt it. I'll talk about that. Also, in terms of non-orthogonal multiple access, not sure whether OFDM is the right waveform in an integration with NTN. And for IoT wake-up radios, again, these are some question marks. And we need them. We need all these things with 6G. But on the other hand, okay, so again, I'm an OFDM lover. So in spite of all my critics, all the bad things that I said, OFDM is not good for 5G, OFDM is not good for 6G. Unfortunately, there is no perfect waveform as of now. I understand that, these, conferences, this seminar series are focusing on OTFS, and many of our colleagues and friends are focusing on OTFS as an alternative solution, but OTFS has more problems than OFDM. AFDM. I mean, I do research in these areas as well from more practical perspectives. So if I look at all the alternatives, currently all the alternatives of OFDM, they are not even better than OFDM. Again, in theory, in the lab, they work. They provide, in the channel conditions, preferable channel conditions, they may provide better data rates, better channel estimation with minimum number of pilots. But in real life, they are not working, They have problems. And some of the problems are listed here: fractional delays, fractional Dopplers, complex equalization, multiple accessing in delayed Doppler domain, and also time variation of delays and Dopplers, RF impairments, and things like that. So latency requirements, MIMO compatibility. I'm not going to go into details, but in summary, in spite of the fact that OFDM is not suitable for 6G, but there is nothing else that's suitable for 6G as well. So we have a problem. We have a major problem. We don't have a waveform that can support 6G vision, 6G requirements. So one of the things that we require from waveform is simplicity and flexibility. If we cannot develop that simple and flexible structure in a waveform, then we cannot make 6G as a success. And all this flexibility and simplicity should come with a receiver agnostic way. So I don't want to change the parameters if there are many possible knobs and parameters that we can change at the transmitter. We want to make sure that all these changes are receiver agnostic. So this is very important. Otherwise, we're going to end up transmitting more data, more pilots, or more control channels, and we don't want to do that. So why do we need flexibility? Because, like I said, 6G has the vision, has the dream of providing service to wide variety of applications, wide variety of channel conditions. So if you don't have a waveform that can support all these applications, all these channel conditions, we are not going to be able to have a good 6G. So from OFDM perspective, 5G multi-numerology OFDM perspective, can we say that it is flexible enough, even though we call it a flexible OFDM or flexible waveform? I don't think 5G multi-numerology OFDM is flexible enough. We only change the carrier spacing, which is OFDM symbol duration, but it comes with a major penalty, which is interference, inter-numerology interference. So we enabled a little bit flexibility, but it came with a major trade-off, with a major issue. So that's why we need to give up on the current multi-numerology OFDM structure. But then what is the solution for that? I don't think we have any solution at this point. Even though, theoretically we can develop, many different versions of OFDM. If OFDM, base OFDM is called as the mother waveform, by changing some of the parameters like pulse shape, filtering, windowing, and how you apply this windowing or filtering, you can generate different types of different versions of OFDM. Similarly, by doing some processing, like DFT processing, you can generate other alternatives of OFDM. So there are some extensions and some flexibilities beyond the carrier spacing, beyond OFDM symbol duration, and these are published in the past. Possibly some of them are deployed by the companies. But again, I don't think these are sufficient and good enough to carry the load of 6G. Similarly, the DFT-spread OFDM, so there is this mother waveform, which is OFDM. We can generate DFT-spread OFDM. That's why we call it OFDM, because there is a pre-coding, DFT pre-coding that we apply before OFDM operation. This whole thing is the OFDM operation. But if you do that DFT pre-coding and then with mapping these spreaded samples into the OFDM carriers. We call it DFT-spread OFDM. But then there are different versions of this, whether you need to apply windowing, filtering, before we, map them to the frequencies. So with these different versions, whether this mapping is going to be a block mapping or interleaved mapping, we can get different versions of DFT-spread OFDM, different derivatives, and some have advantages compared to the others under some conditions. So from that perspective, I think we can say that there are some flexibilities, but like I said in my previous slide, we need to make sure that all these flexibilities are coming with, in a receiver agnostic way. So the flexibility that we introduced should not create additional problems in terms of overhead or in terms of other KPIs. So our solutions, some of our solutions are doing that actually. Some of these solutions are good for one aspect, but not good for the other aspects. So our goal at the end of the day is whether we find a waveform that we can call it mother waveform that's flexible enough, okay, and change some of the parameters of this mother waveform that makes it suitable for various applications, and then make sure that this version of that mother waveform is not conflicting with the other version, because we want to make sure that this lattice, this physical signal can support multiple users. So it's not like Wi-Fi where one user is transmitting at a given time and then occupying all the resources. In the cellular networks in 4G and 5G, resources are shared by multiple users. And in 5G and 6G, not only shared with downlink resources will also be shared by different links. Not only that, these resources will potentially be shared by different transmission points. So that's what makes it very difficult, because if these resources are being shared with different users, with different links, with different transmission points, we need to make sure that the interference from one block to the other block within the signal, okay, this is the whole signal that I'm transmitting or I'm receiving, should be compatible with each other. So this is very important. So if you just decide to use a single mother waveform, like we did in multi-numerology OFDM in 5G, we used mother waveform OFDM, we changed the carrier spacing, and then we basically allocate the resources with this carrier spacing to a user, let's say that ultra reliable low latency user. Another user is using a different parameter, but then these two versions of the mother waveform, they are not compatible with each other. So that's the problem that we had. So whatever you do to generate that child waveform should not create a big interference for the other waveform. So that's basically the strategy that we need to develop. OFDM was not good from that perspective, because in OFDM we were able to generate different derivatives of mother waveform, but those different derivatives were not suitable with each other. So they couldn't really come together and then build that, the total signal peacefully, let's say it that way. And that's the problem that we had. Alternatively, instead of having a single mother waveform and then generating different derivatives from that, and then making sure that they are all peacefully coexisting within the same structure, we can alternatively develop multiple complementing. Complementing is the key word here. So we can generate multiple waveforms. We can use multiple waveforms instead of a single waveform, and then hopefully they can coexist, okay, with each other in the neighboring frequencies or in the neighboring time durations or in the neighboring space domain. So this is basically hyperspace. You usually use time and frequency as the grid points, but you need to generalize it. Space is also something that we use like in MIMO. So we need to make sure that all these different waveforms that we are going to be using for various applications, they have to coexist peacefully with minimum interference, with minimum guard, okay? I mean, if you use a lot of guard to make sure that they coexist, that's not the good strategy. Or we can develop a generalized frame structure. And so this is kind of like a, classical frame structure that we use, classical grid structure that we use. If you can develop a better frame structure, lattice structure that can fit multiple waveforms peacefully, that could be a strategy. So these are the strategies that we want to develop, making sure that all these things are suitable for 6G applications. So if you want to now develop a 6G waveform, the approach is this, okay? So this is the summary. We need to make sure that this waveform is at least the version of that waveform, the derivative of that waveform will have spectral efficiency, power efficiency, should coexist, okay, with other technologies and also with the previous generations, dynamic spectrum usage, given that there are new spectrum allocations. It is sensing capable, and it is multi-connectivity capable, Doppler resilience, channel estimation within that structure is easy, simple, and equalization also is easy and simple, robust against any channel impairments, radio impairments. It has to be MIMO compatible, MIMO capable. Complexity is very important. Many of the time we ignore. And granularity and resolution in different dimensions in time and frequency. So depending on what you are planning to sense, you need to make sure that that waveform will enable different level of granularity, different level of resolution in different dimensions, space, time, frequency, and many other dimensions. NOMA capability is very important. I know NOMA has failed, power domain NOMA. I'm not talking about power domain NOMA. I'm talking about more like a single domain, waveform domain NOMA. So we need to make sure that NOMA is important because in the future, the signals are not going to be orthogonal anymore. Okay, we cannot maintain orthogonality in the future, given that all these new applications, all these new requirements. So non-orthogonality is going to be there, okay, in one way or another. So we need to make sure that when there is overlapping, partial or full, we need to make sure that these signals, overlapped signals, can be separable. And that waveform should support that, whatever the waveform it is. And waveform should also enable analog and digital processing capabilities, because some of the IoT devices will not have the capability of digitizing the signal and applying the FFT, IFFT process. So we cannot assume that. So we need to make sure that some of the radios are capable of receiving signals using analog processing techniques. And whatever you generate, the waveform that you use should enable those analog processing along with the digital, because some users like spectral efficiency, if it's very important for them, they will use digital processing from the same signal, and because they are multiplexing into the same signal. Some other users, IoT users, they should use analog processing. So the total waveform that we generate eventually should be capable of generating and then receiving these different structures with different receiver structures. Adjustable out-of-band radiation, adjustable peak-to-arch power ratio, again, depending on the situation, is very important. And also the waveform should be scalable and compatible with the new frequencies and new channel conditions. So backward compatibility is also important from practical perspectives. So anything that we develop for 6G should be compatible with 5G. Forward compatibility is a must. Anything that we design should allow growth, okay, for the new releases of 6G and also for 7G. If we don't develop a waveform that's forward compatible, then if we come to the next standard 7G, and then we are going to say that, okay, now this 7G waveform should be backward compatible with 6G waveform, and then always this backward compatibility is going to kill us, because we are companies, they are not capable of trashing all the previous standards and then generating a brand new standard. So we don't have that luxury now. It was in the past. For example, we developed LTE as a new standard. We developed GSM as a new standard. We trashed all the analog technologies and we generated a brand new standard. And then we trashed all the CDMA standards, 3G standards, and we developed a brand new LTE standard. But 5G, we couldn't do that because we wanted to have backward compatibility with 4G LTE. In 6G, all the companies are saying that now 6G should be backward compatible with 5G, and that 5G should be backward compatible with 4G. And then when we come to 7G, now we are going to have this requirement: 7G should be backward compatible with 6G, and then that will be backward compatible with 5G, and then that. So that's killing us, okay? Unless we develop a waveform that's forward compatible, so that when we come to that 6G, 7G level, we don't have to worry about this problem. So let me just share a few of the company views at this point. I'm attending the standards and then also looking at the contributions from various companies. These are some of the summaries. So 5G new radio should be as the baseline for 6G, unfortunately. So we're not gonna have a completely new waveform that can trash 5G. That's not backward compatible with 5G. So none of the companies are agreeing with that. Everybody is saying that 5G new radio is the baseline for the 6G waveform, okay? But they allow new waveforms to be integrated into that baseline structure, especially waveforms with low peak-to-arch power ratio, and then waveforms that can support new services like ISAC and NTN, okay? So there is still possibility to include some new waveforms into 6G, given that it has to be compatible with 5G, given that it has to be based on OFDM. But how do we include these new waveforms to OFDM is the key. The core structure is OFDM, but they allow us to add new waveforms that is compatible with OFDM. So anything that we develop for 6G should be compatible with OFDM. This is key. So we need to make sure that if you are working on OTFS, work on OTFS. If you are working on AFDM, or if you are working any new waveform, we need to make sure that that waveform, when you plug that waveform into the signal structure of core OFDM, it should be peaceful. So that should not create huge interference. That should not create new hardware. That should not create new receiver structures. So compatibility means I don't want to change anything, the way that I receive, the way that I transmit, okay? I have to make a very minimal change, and then I can support that waveform as well. This is the key, okay? This is what it means. So backward compatibility is, again, a very strong emphasis, okay? In terms of, waveform, in terms of modulation and resource management, whatever we have been doing in the past, we don't want to change them drastically, okay? Anything that we add should use this, but also add some new capabilities, okay? So OFDM will be the core, and with modification and enhancement. Whether you can modify OFDM and then make it suitable for 6G, I don't know how you are going to do that. There are some, efforts, or you are going to add something into the OFDM which is compatible with OFDM. So that's the key for 6G. Again, power efficiency is important. OFDM is not power efficient, we need to solve this problem. All the companies are agreeing on that, okay? And then also we need to develop mechanisms for wake-up radios, wake-up signals. So you need to use OFDM to generate another signal within the same OFDM structure that can be used to wake up some of the radios that are sleeping. So we need to allow the radios to sleep and then generate signals that can wake these devices, but that signal should be generated within the framework of OFDM. So we don't want to have another signaling or another waveform that's used for wake-up devices. We need to have one mother waveform, which is OFDM, but we need to plug in some capabilities into that so that we can generate signals to wake up devices. Out-of-band emission is very critical in OFDM. We need to solve this problem. Otherwise, subband full duplex is not going to be successful. Subband full duplex is a must, almost a must in 5G advanced and 6G. We already started that. But one of the major problem here is, again, OFDM's out-of-band radiation, especially when we lose synchronization. We can solve this problem by adding a large guards, but that's not something that we want to do. And channel estimation, equalization for linear time varying channels, backward and compatibility and MIMO compatibility is important for any waveform that we are proposing. Another thing that the standards are allowing, channel estimation and equalization can be done in different domains. This is very, very important. So far, we always designed our waveforms in a way that the pilot's training should be within the same domain. If it is time domain, we inserted time domain training sequences. If it is time frequency, like in OFDM, we inserted the pilots in time frequency. But now, with this new 6G, we are allowed to develop pilots or training sequences in a different domain. It could be delayed Doppler domain. It could be in a fine domain. But whatever we design in that domain, when you transform them into time frequency, we have to make sure that it doesn't create interference with the data or with the other OFDM structures. So if we can do that, then this is allowed. And also, all the companies are agreeing that this new waveform should have sensing capability. We need to compare it with OFDM, and then if we can develop something that's better than OFDM, that can sense, that can communicate, we have the room to integrate that into the 6G structure. Okay, so many companies are saying that maybe we need a new waveform for sensing, like FMCW waveforms, or we just generate a pure sensing signal, whether that sensing signal is going to be based on OFDM or not. So companies are discussing that. As I mentioned, analog processing is very important. This is extremely important. The waveform should enable that for RedCap devices or for other IoT devices. Also, like adopting LoRa-like signal structure into the OFDM frame structure could be possible. This is a possibility. Numerology, we are going to give up on that numerology. Like I said, it was a failure. Many companies are agreeing on that. But what kind of numerology, what kind of flexibility that we are going to have, nobody knows about it yet. So we need to think about that. So these are some of the other opinions by the companies. So this is actually, waveform has been heavily discussed, but the conclusion is the community is stuck when it comes to waveform. We don't have a good solution. We have problem, but we don't have solution. That's why, finding a right waveform, proper waveform, revisiting our problem, and then developing, possibly, a good strategy is very important. So these are some of the things that I'm discussing. I'm not saying that I solved the problem. I mean, I myself, in my research group, half of my students are working on waveform. We have a very large group, more than 50 PhD students, and almost 20 of them are working on waveform. Still, we couldn't solve this problem. So this is a very major problem. And companies that are attending the standards, they can appreciate the difficulty of the problem. That's why they are resisting to accept a new waveform. The strategy is to keep what we have, which is working, not perfect. It has many problems, but add some others, okay? Making sure that whatever we add is compatible, and whatever we add will enable future growth, okay? Forward compatibility. So that's basically the summary of the standards. So current major issues in the standards are PEPR. We are trying to solve this using modulation, using waveform, and we are trying to develop some techniques, but this is something that needs to be solved. Synchronization, NTN compatibility, Doppler issue, pilot design and CSI feedback, multi-connectivity, flexible band operation because we have new bands, okay? Coexistence, backward compatibility, sensing support, ultra-wideband operation, wake-up radio, and IoT support. These are some of the current immediate problems that needs to be fixed in the standards. And these are, like I said, the urgent things, channel, estimating the channel, predicting the channel, compressing the channel, sending the feeding back the channel, whatever technique that you use, AI/ML is one of them. And the design of pilots are very critical, so we need to fix this problem. Okay, this is a very important problem. And like I said, from energy efficiency, developing wake-up radios, not only for the IoT devices, all the devices, even our mobile phones, we need to develop a mechanism to keep them sleep more. Okay, we want them to sleep more, but we want to make sure that we can wake them up whenever we need. Not only the mobile devices, we also want base stations to sleep. So in the uplink, we need to develop also signals, waveforms that can wake the base stations up. So both uplink and downlink, generating the waveforms, signaling structures to enable radios to wake up, and then multiplexing all these wake up signals into the frame structure, making sure that you don't wake up the wrong person, you wake up the right person. All these things are very major problems, and we need to solve them. Not only energy efficiency in the radio, but energy efficiency in the system level is important. From that perspective, generating synchronization signals and also enabling the techniques like multiple transmission points are also important. So these are some of the major problems that we are facing right now. Needs to be addressed and fixed right away. Okay, right away means like within a year or so. Otherwise, if we don't solve these problems, we are going to start the standard with a wrong waveform, with a wrong technology, and then that's not going to be forward compatible as well, and then we are going to have a very bad standard. So we need to solve all these problems right away. And there are also other problems that we need to solve eventually in the mid-term, in the longer term. Ambient IoT, again related to the waveform. So there is a signal, ambient signal that we use. So any signal that base station is communicating with a mobile station with your phone is an ambient signal that you are generating. So this signal needs to be used by IoT devices as well to communicate among themselves. So that signal should be suitable, whatever signal that you are generating, okay, between base stations and mobile stations, that signal should be suitable for ambient IoT devices as well. So it cannot be an arbitrary signal, even though people are saying that ambient IoT can use TV signals, radio signals, Wi-Fi signals, any signal out there can be utilized by the ambient IoT devices to communicate with each other. But there is a proper signal, perfect signal, where these devices can modulate their data, can add their data, and then can receive. And that signal is basically the main thing. There is the waveform. It should be suitable for these devices, okay? So again, it's very difficult to design an optimum signal for ambient IoT, because that signal is not designed only for ambient IoT. That signal is originally designed for communication, okay, of the base station with the mobile stations. But a secondary goal of that signal is also to serve that ambient IoT signal. So there are multiple goals, okay? So it's a nested signal structure. So one structure is for regular communication. The other structure is for the ambient communication using the same signal. How do you do that is a challenge and something that needs to be studied eventually. And there are other things like millimeter wave, terahertz, and things like that. So these are the things that needs to be solved as well eventually. I don't know, Shangyang, how am I doing in time? It's already 1 hour, maybe a little bit more than that. I don't. You just tell me when to stop because, like I said, I have more than 200 slides.
Right.
I'm on number
Yep.
28. Okay, so I can continue as much as you allow me. You just let me know.
To be honest,
But if you want me to stop, this is the right time to stop. If you want me to stop, because these are different sessions, this could be probably the right time to stop.
Right. Yeah. Thanks, Hossein. That's a great talk. I think it's perhaps is the right way to stop because we have already passed the 1 hour limit. And but I'm quite interested in what you have designed. You have mentioned, and especially your potential solutions and your methodology to solve this problem. So perhaps we can invite you again for a future discussion if that's okay with you.
Sure, definitely. So the rest of my presentation was basically, in the future, if you want to do this again, let me tell you what are the things that I had in my mind to share with you.
That'll be perfect.
The details that I was going to discuss with you. For example, I mentioned about the reference signal design and the channel models for 6G, because up until now, we always thought that the waveform is designed for sending the data, receiving the data, equalizing the data. Okay, what is the best way of sending, receiving, equalizing? But actually, we missed the point. We are also transmitting reference signals when we are, and often, all these reference signals that we have transmitted in the past, they are transmitted as if it's part of the data. Okay, so with the same structure, with the same mentality, except maybe like modulation was different because we used lower order modulations for pilots compared to data. We use different modulations, but from the grid perspective, from the waveform perspective, from the dimensions perspective, we had the same mentality. Whatever we are using for data, we use the same thing for the pilot. I think we need to change that mentality. And I have enough reason where we need to split the data from the pilot, and then the design of data and pilot should be different. Okay?
Right.
And we need to really think about from that perspective. That's basically what I wanted to discuss more, because pilots are used for many things. They are used for channel estimation, they are used for synchronization, equalization. In the future, it will be used for sensing, it will be used for fire security, and we are using also for MIMO. So we need to make sure that we are thinking pilots as a separate thing, and then we need to find the optimum waveform for that, whether it's going to be in the delayed after domain, it will be in another domain. And then how do we map those pilots into the data?
Exactly.
Data could be in time frequency. The data can still be in time frequency, but the pilot, they don't have to be in time frequency. Where should they be? How should we generate them? How do we map them to the data? This is something that we need to focus, okay? This is a very important problem.
Right.
Another thing that I wanted to discuss is the power efficiency, because that's not an easy problem. It is a very difficult problem. There are many aspects of it. So it is, by itself, it is a session that we can discuss. Like, what are the strategies that we are going to be doing? Currently in standard, they are using DFT-spread OFDM for power efficiency and spectral efficiency. So the same mentality, but I think we need to change that. Okay, we need to develop a new strategy. So there are other things that I was going to discuss, but like I said, I think it's a good point that we stop. and then if there are some question and answers that we can continue with those.
Yes. Thanks again, Hussein. I think it's very nice that you give a very nice summary at the very end that shows there are potential solutions, at least from your perspective, on these questions. In the meantime, we have also received some questions from the audience, and I hope you would not mind answering them.
Of course, I have time. Actually, I have the whole day actually that I allocate.
Thank you so much for that.
The
I
audience
should-
may not have the whole day, but I have the whole day.
Okay, thanks. Okay, to be honest, I think that the questions so far I have received, they are focusing on some specific points, but there are also some my personal questions, especially on the mentality, on your view that a model waveform that supports all the flexibility. I think that's a very good idea. Okay, so I'll go start from the questions from the audience. What do you think? You have mentioned that OFDM is not finished and is actually not good for 6G. And what do you think is the main drawbacks of traditional OFDM that cannot be supporting the integration with NTN and TN development?
Okay, one of the main thing again, in TN terrestrial networks we have cells, and then the coverage of these cells, as you know, can go from like 100 meter to several kilometers. So depending on the cell size, the coverage of the cell, we can call them macro cells, femtocells, microcells, and whatnot.
Right.
But the difference between any of these, if you just take a very small cell and a very large cell, again, the current deployment I'm talking about, yes, there are some differences, very big differences in terms of propagation characteristics, path loss, shadowing, small scale fading. There are differences, but when you look at the differences between any terrestrial base station and non-terrestrial base station, that difference is huge. In terms of channel models, line of sight, non-line of sight, in terms of path loss, in terms of the delays that they introduce. So when you are using OFDM, for example, that supports for both terrestrial and non-terrestrial, even designing the proper CP, because there is no proper CP, okay? I mean, like the CP, is it gonna be with respect to a satellite or it's gonna be with respect to a cell?
Right.
And the synchronization, is it gonna be with respect to satellite or with respect to the terrestrial?
Right.
Ranging is by itself is a problem. So just like almost impossible to have, okay? I mean, it is our goal. I mean, it's our vision to have, a mobile supported by these two extreme transmission point. Let's call it transmission point. It is our goal. It's our vision. But how are you gonna do that with my knowledge, okay, of any waveform? It's almost impossible. Okay, I don't want to say impossible, but it's very difficult.
Yes, I totally got your point, and I personally agree with you. Another question we have so far received is actually also related to the standardization on the waveform perspective. Recently, I know that there is a standardization meeting that has mentioned that for ambiguity functions, which is actually going to be used as the sensing metric for example, for ISAC. So what do you think of this, and how do you think this is somehow guiding the design of OFDM?
Excellent. This is a very, very good question. So when you are transmitting a signal, eventually that's a time signal that we have all this processing that we do, frequency domain, mapping, windowing, and you can do all these magical things. But eventually, a signal at the end is a time domain signal.
Yes.
And if you have a receiver, okay, that doesn't have all these capabilities, okay, of receiving, okay, digitizing, and then going back to the frequency domain, IFFT, and all these kind of things. If you don't have that capability, many of the devices are simple devices will not have that capability, even like wake-up radio signals. Devices. So you really need to generate a time signal that has a very good ambiguity function.
Right.
Okay. So when the receiver takes that time signal and then correlate it with itself, okay, you need to be able to extract that whatever parameter that you are trying to sense, okay, without doing channel estimation. Of course, if you have all this advanced processing, you can go back and then you can do everything in the CSI based. You can estimate the channel, okay, and then from the channel you can do all kind of sensings. You can extract any parameter that you want, but you don't want to do that. You want to do that, okay, without going through all this process. That's why that ambiguity function is very important. So it has to have some structure, okay.
Right.
And then from that structure, the receiver, whether it's a complex receiver or low power receiver, should be able to capture the parameters from the channel, whether it is a timing parameter, whether it's also other parameters. We should be able to do that.
Right. Great. Thank you very much. I have a follow-up
And
question.
also, just wanted to add one more thing.
Right.
When you are doing this, you don't want to disrupt the rest of the communication. So that's the difficulty. So I have a structure where I have all these regular users, okay, enhanced mobile broadband or the other users. I'm populating my data the way that I like. But then I want to add this additional feature
Right.
in my signal where that's the difficulty. If my goal was one user, one application, one thing, I can do magic. My goal is supporting multiple applications simultaneously, multiple users simultaneously, but they have different goals. They have different capabilities. That's the difficulty.
Exactly. Speaking of that, I have a personal follow-up question that I have been also, there are some work, especially from Professor Fan Liu, that we are using random communication signals as what it is for sensing, because for any type of signals, they all have a little bit of sensing capability. What do you think of this? So basically using data to do sensing for ASIC.
You can use data as well. I mean, pilots are easy way, okay, because they are structured, they are designed for that. So you can design pilots, okay, optimized for some parameter estimation, okay, whatever that parameter that you want to estimate. But the data is not designed, okay, with that capability. Data is a random data.
Exactly.
But even if you add the random data, okay, when you transmit, there is still some structure, okay? It's not like white noise, okay? There is some structure, okay?
Right.
Because it is a modulated data used by some specific modulation, okay? So even if you look at the time signal by itself, it may it may look like a random signal with no structure, like a noise, but it has structure. So whatever that structure here, and then however that structure is related to the parameter that you want to estimate, we need to extract that.
Great.
You understand what I'm saying?
Yes, exactly. I totally agree with that. Yeah, and I think, do you think, like, at least from company's perspective, if the sacrificing a little bit in the communication performance, but we have a great improvement for sensing, do you think that's they would buy this idea or not?
I think initial strategy is going to be like that. So main focus still is going to be because the way that the standard is going right now, as if like it is like extension of 5G. Communication is still my main thing.
Right.
So the sensing part of the standard will come later. Okay. So even the waveform, that the way that they are designing, as if like it is designed for communication first. Okay. So the first requirement is communication, even though when we are advertising it, it is a unified sensing and communication. But eventually, I think we will design the communication, okay, make sure that we don't lose anything from communication or minimal. But then we are going to add some sensing capabilities. So it's not going to be fully unified. I think it's going to be integrated again, okay? So sensing is going to be integrated into the standard later on. And of course, there we have flexibility. We may add some new waveforms. We may introduce some new training or pilot structures. So there is a room still to do that.
Totally agree. Thank you. Okay, another question is actually, personally, I think is a very difficult question for the waveform design in general, especially concerning OFDM. You have mentioned that energy efficiency and the PIPR are very important, and but also how to suppress out-of-band emission and especially under the subcarrier full duplex. Do you have any solution to that?
Yeah, I mean, like these two problems are not independent from each other. So if you don't solve the PAPR, if you just use power amplifiers, and then if you push them into the nonlinear region, automatically you are generating additional out-of-band emission. So, but even if you don't just use, I mean, like power amplifiers, just imagine that you don't use power amplifiers, you don't have any nonlinearity, but OFDM comes with out-of-band emission because of the sink side lobes.
Right.
So I can solve those side lobe problems, as you all know, with windowing, with filtering. So I can basically, compress the signal, in spectrum. But of course, that comes with some penalty, spectral efficiency penalty. But even if you do that, let's assume that you did that. You generated an optimum signal, minimum side lobes. But then you push them into the power amplifier, and then because of the peak-to-charge power ratio, then you get that regrowth. Everything that you did, everything that you optimized, now you are going to regenerate those out-of-band emission because of nonlinearity issue. So you can't just say that, okay, I want to design things independently. Even now in the standards, it's very surprising. All these companies, all these highly intelligent people, they divided this peak-to-charge power ratio problem into two: modulation and waveform. Modulation people are working independently from the waveform people, and then they are developing this classical modulation is QAM modulation. They want to basically change it, either the constellation, geometrically or probabilistically. They want to change the constellation of the QAM in a way that the new QAM,
Yes.
this new QAM will have less peak-to-charge power ratio. But they are doing this independent of the waveform.
Oh my God, I see.
Whatever you do in the modulation, if you are still using OFDM, it's a waste of resources because it's not going to work in OFDM, but it can work in DFT-spread OFDM. But then in DFT-spread OFDM, we also have the peak-to-charge power ratio problem. It's not like DFT-spread OFDM has a perfect constant envelope. It's not like that, DFT-spread OFDM has also peak-to-charge power ratio. But when you are developing a modulation, you cannot do this independent with the waveform. It has to be done together. So we are not designing that. In the standards, you will be surprised that these groups are working independently, and both of them are trying to solve the problem. But that problem is going to be regenerated later on.
I see.
So unless you do it jointly. So going back to your original question, out-of-band emission and peak-to-charge power ratio are not independent problems. They have to be solved together.
Yes, I agree with you. And I think I'm actually a little bit motivated from your answer. I mean, that's actually
you should be. Xiangyang, you should be. Right now, the wireless community's number one problem is the waveform problem. Many people are thinking that, physical layer is done. No, I mean, like if you don't solve this problem, you won't even have the whole standard, So that's why we got our proposal accepted in SNS, in our joint proposal. Because I was writing another proposal with another professor, and then we had this waveform part, and then the professor came to me, Dr. Aslan, looks like the waveform is already decided in 6G, and then probably there won't be any waveform research in the future. Shall we drop the waveform part from the rest of the proposal? And I said, no, the waveform part now is more important than ever because that problem is not solved. Right? I mean, it's something that needs to be solved.
Exactly. And as you mentioned, there are actually some very urgent things we need to provide some solutions. Yeah, I think that's very important and motivative.
But unfortunately, Xiangyang, these people who are really designing the standards and then looking at those applications or other aspects, They don't know how critical the problem, because they are underestimating the importance of the problem. They are suggesting that we need to have multi-connectivity, but they think that they can do it with the current waveform, okay, with the current thing. They are suggesting that they need to have MIMO, massive MIMO, and then they think that we can do it without having the proper waveform, with the proper channel estimation. They are suggesting, NTN and TN unification. They think that they can do it without proper waveform. Many of the things that they want cannot be done.
Exactly.
And they will realize that later on. That we need to warn them ahead of the time. Look, whatever you are going to build later on is not going to be success. That's what we did in 5G. We said that we want multi-numerology, right? But they couldn't figure out the energy, the leakage problem and near-far problem. And then later on, they decided that it didn't work. Now they're going to give up on that. The whole 5G became affected by this decision of multi-numerology, and then we failed.
Right. It's very interesting. It's very interesting perspective that you have just mentioned. I also personally feel that the academic society is a little bit isolated from the industry, and it's really hard for us, at least for me, to have a spot on the real problem that are pushing back our development on the waveforms.
Let me tell you, if for those academic community, let me tell you one sentence, okay? That's going to be very, very critical. If you really want to do something outstanding, you just have to understand that the real life is not going to give up on OFDM, and then they are not going to replace it with any other waveform. Unless, of course, there is a magical waveform that can do all these things, but I don't think there will be a magical waveform that can do all these things. I mean, like, we have to be honest with ourselves. We need to make sure that whatever we do, whatever we develop, should coexist and be a friend with the OFDM structure.
Exactly.
Structure, I'm saying, okay? It has to be friend with OFDM structure.
Yeah, totally agree. I think I just have one last question, given the time limitation, that is synchronization problems, especially when we are having this NTN or massive IoT. Do you think the current OFDM there's new advancements or any other type of algorithms can solve this problem?
With my limited knowledge, this is a huge problem. I mean, like, I focus on the other problems, energy, this and that, but really the most important problem possibly is the synchronization. Again, given that we want to have multiple transmission, multiple receivers, okay? In the past, in the old days, we had one transmitter, one receiver, like Wi-Fi. One transmitter, one receiver. OFDM is beautiful, okay? You can make it work. Cellular, one transmitter, multiple receivers, multiple transmitters, one receiver, base station and mobile stations.
Yes.
With proper synchronization, ranging, and all these kind of things, we made it work, okay? 6G, multiple base stations, multiple mobile stations. They have to all work, communicate with each other. This is not easy. Unless everything is uniform, cells are uniform, the distances are uniform, and this still it's problem. But now you're talking about NTN, multiple transmission points and multiple users. I mean, just not easy. I'm not saying it's impossible, not easy. OFDM is gonna fail there. It's gonna fail there. But they want it. I mean, they want it. They say that, we want this, but they don't know that they can, they're going to hit the rock, okay, when they start implementing this.
Exactly. I think that's a very, very great answer. And personally, I agree with you. But previously, I was, as you have mentioned, that for some of them, including myself, that we are focusing too much on some new waveform designs, but we did not give a full respect to OFDM and the fact that we are going to continue using OFDM. Yes, I think that's a great takeaway for, at least for me.
But you don't miss that thing. I mean, like, keep OFDM, add that new thing. Okay, we don't want to just, OFDM is not the future. We need to understand that. We need to add that thing there. Okay, that's gonna be new. Okay, so that's hybrid thing is the key thing here.
I agree with you. I agree. Okay, Thank you again, Professor Arslan. That's a very great talk, very motivative, and I'm excited to work more. Thank you very much.
Thanks for the invitation. It's a pleasure to be here, and then we'll be in touch.
Yes, and I hope that we have the opportunity to invite you again for the rest of the presentation. Thank you.
Sure. Like for those who have questions, who wants to collaborate, who wants to ask, like my emails, WeChat, everything was in the first slide. I don't know whether I need to put that there, but I think they can always go back and then see it. So this is basically, how you can get in touch with me. Okay. And it will be my pleasure, to collaborate with, again, I don't know who is out there, but if you need, to learn a little bit more details about any topic, please let me know.
Thank you. Thank you, Hussein, for this very welcome to all the collaborations. That's very important for all of us. Thank you very much.
All right.
Okay.
Okay. Thank you.
Next time. Bye-bye.